Will we ever achieve a theory of everything? One that explains all of reality from the smallest quantum phenomena to the largest structures in the universe? That's been the holy grail of physics for over a century. But according to Princeton cosmologist and Nobel laureate Jim Peebles, the answer is probably no.
If you have an idea, I urge you to try thinking about it, but do keep your day job.
In fact, Professor Peebles argues that physics can never deliver perfect certainty. Not because science is failing, but because that is simply not how physics works. His new book, The Physicist's Way, a philosophical guide to the practice of physics, distills a lifetime of insights into what physicists actually do when they do physics. In his book, he grapples with questions such as, if we can never reach a final theory, then what is the goal of physics? And if certainty is impossible, then what does it really mean to know something scientifically? Recently, I had the distinct pleasure of sitting down with him to discuss these ideas. Thank you, Dom and Amelie and the clubs for organizing this event. I'm so thrilled to have the opportunity to talk to Jim today. A couple years ago, I think it was, at one of the physics holiday parties or something like that, I ran into Jim and I asked him, as I always like to do, what are you working on these days? And Jim triumphantly declared, philosophy. And I was like, what? I was expecting him to say something like, oh, tidal forces on galaxies or something like that. So I asked him, of course, tell me more. And so he said, well, over the years, a lot of people have reached out to me and saying, how can we take you and your cosmological theories seriously when you can't even tell us what dark matter is? And so this is what I'm thinking about. How do you answer a question like that? And so I've been, dying to pick your brain more on the matter. So now that I have you, Jim, what is dark matter?
I don't know.
Why did you start writing this book? What are you hoping to?
I didn't start with any plan of this sort. Through the years, though, of teaching physics to graduates and undergraduates, I came to sense the feeling that many of you people would like to know whether there's a plan behind the choices of the courses we present and the kinds of problems we ask you to learn to solve. Is there a plan? Is there some background thinking that shapes your thinking? And of course there is, and I choose to call it a philosophy, though it isn't anything like the philosophies you will learn about in the philosophy department. It's much simpler. An example, at a colloquium, it has happened in Heidelberg, Germany, I happened to remark, well, all of these theories are made up by people. Who else? One of the faculty members there, I was not aware then of the fighting words social construction. He said, but you can't say that. A social construction is something that people make up by artificially invent. Our physics is based on reality. Well, what do you mean by reality? Well, I mean, of course, the evidence. The debate went on for quite a while, and later one of the undergraduates wrote to me saying, I really liked that debate. And I thought to myself, well, I liked it too. And that, among other events, led me to think, yes, there is a philosophy behind physics, and I think I can write it down. So I started beginning with a short 10-page article that I put on the archive, which contains research papers that have been published, sometimes research papers that are under development and you want some feedback. And that was what I wanted for this essay on a philosophy of physics. I got a lot of feedback from philosophers. No physicists. Anyway, the feedback helped. And I continued to think about this and to develop thoughts about it. And it grew into a manuscript that became big enough to be a book. A thin book, but a book.
Very enjoyable book. So I'm curious to hear your thoughts. Stephen Hawking is famous for saying a while ago now, if we do discover a complete theory, we could then discuss the questions of why we and the universe exist. And if we answer that, it would be the ultimate triumph of human reason. What are your thoughts on that? Is that possible?
Well, Stephen is a wonderful person, brilliant, despite his deep handicap, an inspiration, to many people. But I don't think, we're not going to be able to, it's a much simpler question. What makes a fruit fly work? What is the quantum state vector for an isolated fruit fly? And for that matter, can a fruit fly really be in an isolated state? Or is it so entangled with the environment that that can't happen? These are questions that are impossibly complicated, let alone who invented the world, or whatever Stephen meant by the ultimate reality. I bet there is an ultimate reality, and I bet we'll never find it. We'll only be able to find good approximations to it.
Okay, so you're saying that there's two claims. You're saying that there is an ultimate reality.
That's an assumption.
That's an assumption. That's an assumption, and that we'll never find it.
Right.
So why do you think that there is one?
It might be classified as a hopeful guess, but we have evidence of it. We have theories, some of which work remarkably well and remarkably deeply into the properties of matter. Why should that work so well if there isn't some ultimate theory that we're approaching?
Can you give us an example of what would you say is?
Well, consider Maxwell's equations.
Okay.
They're spectacularly useful, and they are spectacularly successful descriptions of reality. Of course, they're only approximations, but they're very good ones. You can go to a waterfall in which the mechanical energy of falling water is turned into electromagnetic energy by the laws of Maxwell's equations. That energy is transmitted as a field, electromagnetic field, along transmission lines, divided up, sent to your home, where it will cause the doorbell to ring. It's physics. It'll charge your cell phone. The cell phone will receive information by microwave radiation of the time. It'll show you the time. You will ask it a question. It will send out the question. All of that is just Maxwell's equations. Of course, in the cell phone with a mixture of quantum physics. Deeply important, electric vehicles, so important, and they're just Maxwell's equations and chemistry to account for the energy stored in the batteries. And yet, of course, it fails when applied to an atom. That doesn't mean Maxwell's equations are wrong. It means that although they're a very good approximation, they're incomplete. And so, of course, we have a better theory, quantum physics, but of course it's incomplete too. From quantum physics, you will go into the weak interactions which merge weak interaction with the electromagnetic interaction. They're part of the standard model for particle physics. But everyone who thinks about this seriously is sure that our standard theory of particle physics is an incomplete approximation to a deeper theory that probably is an approximation to a still deeper theory for all we know. That's the nature of physics. Rigidly successful approximations, but always incomplete.
Okay, so how do we get better explanations? Like how do we, you're saying it's all approximations. What does a physicist do?
Well, of course, there are two aspects to what physicists do. They think up theories, then they test them.
Okay.
Simple as that.
Okay. That sounds pretty simple to me.
Well, of course, it is more complicated.
Where do theories come from?
Oh, well, we don't have a theory for that. An example, Einstein in 1915 published a theory of gravity that he had been working on for almost 10 years. The theory, he decided, is now complete. Of course, it's not, because it doesn't handle quantum physics. But that physics was considered beautiful. It was widely acclaimed, and it became part of the standard theory in textbooks. But it was never an established theory. For example, the Nobel Prize Committee didn't mention general relativity when he was awarded the Nobel Prize, 1921, I think it was. They mentioned his contributions to quantum mechanics. That was more than ample to justify the prize. But general relativity, although a beautiful theory, was not well tested. In fact, until the 60s, it had three classical tests. One was the anomalous motion of the planet Mercury. That is a successful test, but it wasn't entirely a test, because 10 years earlier, Einstein had set out to find this theory and expressed the hope that it would account for the anomaly in the precession of Mercury. Now, I'm not suggesting that Einstein stopped looking when he found the theory that accounts for the anomaly, but if you're being careful about evidence, you have to say, well, subconsciously, how did that brilliant genius know he had stopped? Was he not influenced a little bit, at least, by the success in accounting for the orbit of Mercury?
So would you say, though, that the fact that there was this discrepancy in Mercury's orbit, so just to maybe we should explain a little bit about, so what happened is, I think I've taught many of you elliptical orbits in, I think 105, we're doing it right now. So Kepler's first law says that the orbit is elliptical, right? And that the orientation of the ellipse doesn't change over time, that it's a closed orbit, right? But very precise measurements that were done in the 1800s showed that the orientation of Mercury's elliptical orbit actually was precessing over time, that the location of the perihelion was like itself rotating by an incredibly small number. It's like 1% of a degree per century or something like that. Okay, so something insanely small, okay? But they found this discrepancy from Newton's laws. And so would it be fair to say that it was this discrepancy, the failure of Newtonian gravity to explain this phenomenon that actually maybe inspired Einstein to look for a different theory?
Well, I don't actually think so.
Okay.
I think he had a deeper thought, a beautiful thought. It was known then that the gravitational accelerations of test particles are very close to the same, independent of the nature of the particle. Why should gold and aluminum fall at the same rate? Well, there's an easy explanation. Suppose the test particles are moving freely in a straight line, but we're being accelerated. If I'm measuring this motion, I'm sitting on a chair that's pushing me. And so gravity is really me being pushed rather than the particles being shoved. It's a beautiful notion. It requires, of course, curved space-time, and his big struggle was to learn how to characterize space-time curvature and then set up the equations that produce the curvature, that produce the motion that you observe, including the motion of Mercury. It was beautiful, but I was mentioning the tests, and the fact that general relativity satisfied the observations of the motion of Mercury was not entirely a test. And it said, maybe some of you know the Just So stories of Rudyard Kipling. Well, they're so absurd. You know them?
I've read a few.
Okay, Just So stories. Now, the stories are silly, how the leopard got its spots, how the elephant got a trunk. Apparently its nose was caught by a crocodile.
I think it was something like that.
A Just So story. Well, consider that Einstein, a brilliant, inventive person, spent almost 10 years looking for this theory. How do we know that he got the right theory or a good approximation to the final theory? Maybe it's just a Just So story. How do we know that Einstein hadn't just invented a Just So story? Clever person, you'll make up a story that fits what you want to fit. Well, of course, the answer is you look for tests. the three classical tests were really very, very poor. But it started in 1960, I might notice right here in Princeton University, by Professor Robert Henry Dickey, Bob to all of us. Just to mention the tests, I mentioned the motion of Mercury, so we see that situation. Gravitational redshift. If light comes from the sun to us, it's the frequency levels of the lines that are emitting radiation will be shifted to the red as the gravity slows the orbit, so to speak. That's a prediction. Very difficult to test because the motion of matter on the surface of the Earth, of the sun, is moving around, so there are Doppler shifts. Overcoming that problem was a graduate student project by one of Bob Dickey's students, whose name will come to me. He found out a clever way, he and Bob Dickey, to measure it, and he got a test of the prediction to 10%. At the same year, the Mossbauer effect was used by Pound and Rebka at Harvard. An atom may emit a photon, and the photon will rush away carrying momentum and energy. The atom will recoil. That means that the photon is not carrying the total energy of emission of the transition between the two lines. Part of it goes to the recoil of the atom. And that means that gamma ray encountering another atom of the same kind will not be able to knock the atom from the ground level back up because it doesn't have enough energy. But if you put that atom in a lattice, then quantum mechanics tells us that the whole lattice can recoil. And the recoil for the whole lattice is so tiny because there are so many atoms that in fact the gamma ray doesn't lose energy, and it can be absorbed by another atom over here. But now suppose you put the emitter up in a tower and the absorber down below. The gamma ray, as it falls, is going to gain energy according to general relativity. To find out how much energy it is absorbed, move the detector down slowly. That's a Doppler shift. And if you move it at just the right rate, then the gamma rays will be absorbed. So you look for that absorption. The motion you require gives you the redshift, and they also got a 10% measurement. But 10%, and also it was thought that there is a nearby star cluster, two stars in a circular orbit. One of the stars is a white dwarf. It used to be more massive. It exploded, lost a lot of mass, but it was still massive, comparable to that of the sun. But it's moving in an orbit with another star that's on the main sequence. Now, look at the spectrum of the light from the white dwarf, and you ask whether it is redshifted by gravity. Now, of course, it's redshifted by the motion around the other star, but you can take that into account. Because that white dwarf is a mass comparable to that of the sun, and it's very much smaller, it's a much bigger redshift, and one that you could hope to measure. Reports of that measurement pre-war gave a theory and an observation that agreed, but both were wrong by a factor of 4. That was not skullduggery. That was just people doing adventurous measurements and trying to get a handle on a difficult problem. That got straightened out, first by Bob Dickey and Pound and Rebka, and then far more advances. But that was, of course, much later than we're talking about. The final measurement is that light from a distant star passing the sun gets deflected. That measurement is very difficult, but it had been done many times prior to 1960. And I think it's fair to say that they had it to 30%. 30% for a deeply fundamental measurement, that's awfully scant. It wasn't until the 60s that the technology developed that could test general relativity. Now, of course, there are a lot of tests well advertised the detection of gravitational waves from merging white dwarfs. Brilliant. But there are others. Let's not get into the details, except to notice that general relativity could be used to construct a theory of the evolving, expanding universe. There are lots of tests of that, and the tests jibe with the observations, convincing us of that. I got onto this because I wanted to say, why do we say that a theory is not just so story? It's because it makes predictions that can be tested and found to agree with observations. That's the whole game. Well, of course, there are lots more games. You know the physics, apply it to things. That takes a lot of skill and ingenuity. It produces lots of advances. But establishing this theory, the game is, show me it's not a just so story. It's not no, it's not that, because it gives me these predictions that agree with these observations. Why would that happen if it were just a just so story? It's got to be more than that. It's got to be an approximation to reality, assuming, of course, that there is a reality.
Yeah, so the key thing, you mentioned these 3 different tests, and I think what's really significant that it's not a just so story is that these are independent tests. They have nothing to do with each other.
Right, please don't mention the 3 originals. It's the 3 classical tests. The other tests,
Yes.
the gravitational wave radiation,
Yes, yes.
gravitational waves. It's important that these look at the theory in different directions. But sometimes an observation can be both crude and critical, as in detections of particles. They're well predicted, but that's a minor point. The key to this is predictions from independent methods really impress us. Actually, should I show an example?
Sure.
I happen to have brought a harp. I'm going to play it. Can we read that? The speed of light. Notice some of the early entries. Romer, Bradley. These early guys, one that is easy to explain, Fizeau, 1849, had a mirror set up 8 kilometers away. He had a rotating wheel with notches in it. The notches let light from a very bright source shine through, travel to that mirror, and come back. This wheel of notches is rotating. And if it's rotating at just the right speed, then the light that gets through one notch, as it returns, will get through the next notch. You know how long that took? You know the distance, you get the speed of light. Rosa and Dorsey. Electromagnetism gives us 2 units, units for electricity, units for magnetism. Maxwell unified them. But you have the 2 units, and the 2 units define the speed. At the time of this measurement was suspected to be the speed of light, later shown to be that. But they got a very different method, gave a velocity of light that's very similar. I like the fact that this person, Charles Sanders Peirce. Now please understand that this is from the days when men were men and women were not understood. So when I come across loaded words in here, please feel free to hiss, but also pay attention to what this guy says, because he really understood physics very well. All the followers of science are fully persuaded that the processes of investigation, if only pushed far enough, will give one certain solution to every question to which they can be applied. One person may investigate the velocity of light by studying the transits of Venus and the aberration of the stars. Another by the oppositions of Mars and the eclipses of Jupiter's satellites. Eclipses of Jupiter's. A third by the method of Fizeau, I mentioned that. Another may follow by the different methods of comparing the measurements of statical and dynamical electricity. Statical means electric, and dynamical means magnetic. They may at first obtain different results, but as each perfects that method, and that procedure, the result will move steadily together toward a destined center. He didn't know that, but this was published in a journal called Popular Science Monthly. I was delighted to learn that Popular Science Monthly changed its name to Popular Science, and when I was a kid, I used to buy copies of that magazine and read it cover to cover, articles and advertisements. Raise chinchillas for fun and profit. Plant zoyosa grass, you will never have to water it again, and on and on. It may be what I am today, I think. Pierce was rather a complicated person, interested in get-rich schemes, from a well-to-do family that provided him with jobs, but they're always, what are we going to do with Charlie? But he did have very good understanding of what physics is all about, written in this journal, Popular Science Monthly. This is an extract. To go back, you notice many other measurements. As Peirce guessed, thought, the measurements become more and more precise, but each agrees with the previous. Why are these different methods of measuring one quantity giving such similar results, considering the great precision of some of the recent measurements, yet you get time and again the same speed? Surely that's not because the speed of light is an artifact, an artifice, just a social construction. It's got to be something to do with reality. A test.
Yeah. So the thing, I think, seeing this sequential improvement, over the centuries, seems very convincing that there is something that you're approaching. Why can't we say, we found it. We know the speed of light is, that, and that, well, obviously now we've defined it to be that number, but, you're also claiming that we can never know for sure that we know everything, that we have reached the end point. So what would potentially the next step be here? Like, what is not known?
Well, I resist. What is not known is not known. But all of these tests have limited precision. And so we don't know what would happen if the precision were increased still more. We go into let's not bother about the technology, the reason for making the speed of light an artificially defined number. The tests are meaningful, but they don't amount to a theorem. We don't do theorems in physics. We can't. We are very proud of some of the things. We could say, you can't build a carburetor that will double your mileage. You just can't. It violates the laws of thermodynamics. And thermodynamics is very well tested. But of course, it's not a precise, it's not a theorem. Thermodynamics is of a limited precision. And do we know that some magical trick? Well, I don't believe there could be, but we don't know this for a theory, for a theorem. And that's why I think we should be always a little bit careful in celebrating the great precision of physics. It's of limited precision.
Mm-hmm. Yeah, or like the idea that the speed of light, this is something that, we teach in special relativity, which again, many of you are going to be seeing very soon or have seen, that, the speed of light is the same in all reference frames.
Yeah.
Right? We believe that to be true because it has, so far all experimental tests are consistent with that idea.
Right.
But can we say that it will forever be true and that we'll never find a deviation from that theory?
Well, and another side of the coin is people are working very hard to try to find a unified theory of particle physics. Particle physics is a set of theories that all look elegant, very successfully, but they don't all fit together. A unified theory, maybe one based on superstring theory, M theory, and all these other ideas of modern, deeply theoretical physics, could lead us to something better. And that something better may show us that the speed of light is really a construct built out of more elementary phenomena, concepts. We just don't know that. So far, it's C is C and all alone, but who knows what the future will bring. There certainly is room for a deeper theory than quantum field theory.
You've been mentioning Bob Dickey a lot, and there was one quote that you wrote in your book, which I actually laughed out loud when I read it, which is that he said, if you want to do an experiment, don't be daunted by the untidiness of the theory.
Yes.
Just go ahead and do the experiment.
Yes.
And the reason why I found this so kind of refreshing is because many times we think of the theory as being the pure, the beautiful, the clean, and the experiment as being untidy and messy. And I'm sure a lot of my students here would agree with that.
And of course it's true. A good experimentalist has to have some of the aspects of a craft. You need to know so many things, many little details, to do a brilliant experiment. In that sense, it is messy. But of course, without the experiment, your theories are all just so stories.
Yeah.
So
the experiment is the reality.
the experiment is the approximation to the reality.
This is, a transition that happens in the brain, in a physicist's brain, I think. When you're saying that this is what physicists do, we have theories, we create them. Do we create them or do we discover them?
We invent them. No, of course. Discover, you didn't find it under a rock. You invented it.
You invented it.
No, I think that's accurate.
So we invent theories, usually, influenced or inspired by observational data.
Right.
Like Einstein, even though he didn't have data for GR, he still was, perplexed by the idea that two completely different masses always follow the same
Yes.
acceleration,
That
which is a
was-
really perplexing thought. As you said, I remember when I first heard that, when I first learned that in school, we were, of course, just told that as a fact. All objects fall at the same rate. I was so skeptical of this that I ended up in the emergency room. I set out to test this theory.
Why did you drop? You?
Well, I ended up being myself. But that was not intentional. No, it was in first grade. I was 6 years old. And our teacher in school told us, they went to the moon. They dropped the feather and the
rock.
hammer, and they fall at the same rate and everything. And I was like, but that doesn't make any sense. Like when I drop a feather and a rock, they don't fall at the same rate. And so I thought, well, maybe I just should, maybe if I go higher and drop them at a higher height, the feather will catch up with the rock. I mean, I don't know. I've never done it before. So I climbed a tree and I tried. But I ended up falling out of the tree. I did hit the ground before the feather, though. But anyway, it is a very, you start with like this perplexing question about nature, like why do objects fall at the same rate when there's no air resistance? And then you come up with a theory like GR, General Relativity, and then of course, in order to turn it from a just so story into what we call an established theory, is by testing it with independent experiments, and that's essentially what physicists do, right? But you're not born knowing how to do that, right? You have to learn.
Oh, yes.
And I think there's many misconceptions in the non-physics world or non-science world of what a theory is. We often hear, we know that quantum mechanics is true or something. We know, and so you learn these as facts, and then, but that's not real physics, right? Physics is the process of creating better approximations. So for you, I'm actually really curious. Do you remember like how you went through from your undergraduate days in Manitoba, and you were learning all these theories until eventually, of course, you became one of the people who were creating and testing other theories? Like, how did you transition? How did you make that transition?
Well, of course, always, certainly for me, it was Bob Dickey. He had decided that we could probe the properties of gravity far better with the tools we have when he began this work in the late 1950s. We had a theory of gravity, general relativity, but it was poorly tested. How do you test it? Well, of course, there's ways to think of that. He was inventing. When I came and joined his group, he had a stable of at least a dozen people doing experiments on the lab table to test gravity physics. For example, he had one person whose name, Lloyd Kreutzer, I haven't seen the name in decades, but there came a tank full of a fluid with two spheres of material, one with a high atomic weight, the other with a low atomic weight, but so filled that they had the same gravitational mass. You put them into this tank with a fluid that is adjusted to have the same density as the densities of the spheres, so they'll both float. But of course, there can be a difference between the force of gravity that is pulling the bodies down and the gravity that is responding to the push of the fluid up. One is a force due to pressure, the other is a force due to gravity. So do the two spheres float at exactly the same rate, or does one go up and the other down when they have the same mass and radius, so the same density? Standard theory says no. But of course, that's standard theory and it isn't well tested. Let's do it. And of course, you could get very exquisitely precise measurements by adjusting the masses of the two weights and the atomic weight and the mass density of the fluid. Add a little heavy salts, you make the fluid a little more dense, and so on. It was an experiment to test an idea that is theoretically excluded by a theory you don't trust. And that, of course, made all the difference.
So what you're essentially saying is a test for the equivalence principle.
Yes.
And a lot of people here have done. One of the labs that we do in 105 is a test of the equivalence principle with a pendulum.
With a pendulum, yeah.
And two different masses.
Yeah.
Okay. But yeah, I think hearing this example, hopefully, is really eye-opening, because it's not, when we're asking you to do things, it's not just, verify a theory that's known. I think that this is a very common approach to undergraduate labs.
Which sounds so dull. You know the answer.
You know already the answer. Yeah. But this is really, this is real physics, is asking a question that you don't know the answer to. And even now, decades after that floating sphere experiment, we have increased the constraints on our big G.
Yeah.
And to however many significant figures, I don't know what it is now, like 15, we think that it's the same for all objects, but it might not be, right, at higher
That's right.
precision.
Pardon, 10 to 15 is about right.
This is unknown.
Well, of course, at the limit of precision, everything is unknown.
Yes.
And we hope can be better known, and we hope can fit into a better theory. So one big search is for a better theory of gravity. And in the book, I spend a whole chapter on the fact that we don't have a unified theory of large-scale physics described by general relativity and small-scale physics described by quantum physics. We are so proud of the thought that there is an objective reality, and that we can approach that objective of general relativity. We can good approximations to it. Yet we have two theories at the moment that are different, that point to different objective realities. That's really a shock, isn't it? I began that chapter with a comment on C.P. Snow's Two Cultures, because C.P. Snow was commenting on the fact that the physicists don't talk to the literary arts people, and they don't talk to each other. And isn't that a shame? Surely there is a unity to be found. The ant biologist, Edward Wilson, wrote a book. It's called Consilience, and that just means that you got a lot of different evidences and they all point in the same direction. But he wanted to get to the point of a consilience between the two cultures. I don't think it's going to happen. We just have different brains. But certainly we think there's a consilience in physics, in physical science. But we haven't found it.
Not for GR, not for the large-scale gravity and the small-scale quantum mechanics.
Now, of course, one of CP Snow's complaints was that you people think in two different ways. Can't you get together? And I somehow can't get rid of the thought that we have the physicists who know large-scale structure and the physicists who know small-scale structure, quantum physics and general relativity, and we each think in our own way. If we somehow could think in just the right way, could we bring these two theories together? If you have an idea, I urge you to try thinking about it, but do keep your day job, because people have been struggling with this thought since the 1950s without success. A notable physicist, Eugene Wigner, was willing to speculate that, well, okay, they're just do physics. Live with it. If you go to large scales, use general relativity. If you go to small scales, use quantum physics.
Well, surely in nature there must be a place where these two
Intersect.
There
are examples. You know that the GPS system has to use general relativity in its predictions of the motions of the satellites that tell you by their communication with your whatever it is, where you are. But you need to know where those satellites are. And to keep track of them, you need to use general relativity. But that's a tiny correction. I do not know of a place where the two get together.
I mean, what about at the event horizon of a black hole?
Yes.
You can't access it.
It's a little hard to get at.
But I guess I'm differentiating here between what we have the technology to be able to do versus this mind-independent reality that you refer to. Surely there is some place.
Well, there could be, about the gravitational wave detection and about the fact that these are thought to be produced by the motions of two massive particles as they spin together and shake the gravitational field and produce these waves. But there are other waves potentially possible that would be produced in the early universe by quantum fluctuations in space-time curvature. This is a fundamentally quantum effect. These waves have different polarization from the waves that are produced by merging black holes. And if you can detect them and convince yourself that they really do have the property of the waves that are produced by quantum physics in the very early stages of expansion of the universe, then you would have just that joining of the two theories.
Yeah.
There was a time, about a year ago or so, when people thought they had it. We had a couple of very excited talks by the maximal theorists here at Princeton saying, oh, this is wonderful. Here we have quantum mechanics and general relativity together. But then the experiment went away. No complaints. They were trying hard. They thought they had something. You got to tell people about it, but they didn't. And so there are new generations of experiments that are looking at this effect. It would be dramatic.
Yeah. So there are a few elements, I think, to what you're describing of what a physicist does and how a physicist thinks. And that's the essence of, we often hear like, oh, you need to learn how to think like a physicist. And that's kind of considered by some people as a positive thing
Yeah.
and something to strive for. And the elements seem to be this idea that, there's a certain humility about it, that, we acknowledge that we can't know everything, that we don't know the whole story. And then there's also this kind of this confidence to be able to have better and better tests of the theory.
Yeah.
As an educator myself, I'm very curious as to how does one learn how to think like a physicist? And so I'm curious what, how do you, at one point in the book, I forget who said it, but you say you can learn theoretical physics from a book,
Yes.
but you cannot learn experimental physics from a book. You've got to just do it, right?
Yes.
So yeah, when are students, like, are we teaching students as undergrads? Are we teaching them the real physics?
Well, a good approximation to it, of course.
It's a first order.
It is ironic that we teach undergraduate physicists the standard law of physics.
Yeah.
We expect them to be able to answer questions about this standard physics. But they are then released to graduate study in physics or some other subject, and they're required to solve problems to which they are not assured that there is a solution. Whereas, of course, up to that point, any problem they're given, unless the instructor makes a terrible mistake, has a known solution. It's a shock.
It's a shock.
What are you giving me a problem like I don't know if there's an answer to this problem. What am I to do? Well, get to work.
Yeah, I think that that is a shock, and I do believe there is a way to bring more of this real physics
Yes.
at an earlier stage.
Yeah.
Yeah, I think it would be really curious to hear what all the students, many of you have, been my students or in other labs, and because you can't learn physics, you can't learn real physics from a book. You have to do it. You have to get your hands dirty. And I actually remember how one of the transitioning moments in my education when I kind of had this, where it was in graduate school, and one of the first projects that my PhD advisor, who's here, gave me was to build like a testing station for like these little feed horns. And I had to, test like 250 of them one by one. It was like really tedious and really boring. And I was there for like hours and hours in the lab. And I was, at one point I was thinking to myself, like, I started studying cosmology because I wanted to understand, the mysteries of the universe. And I'm here in the lab, like measuring feed horns. Like, what am I doing with my life? And this was, it was late night in the lab. And my advisor came by at around, he would often come by in the middle of the night. And so I think he felt that I was feeling frustrated and dejected. And so he went on a little like rant about experimental physics. And he was like, understanding these feed horns, the light that comes from the sky has to go through the feed horns to get to the detector. If you don't understand the feed horns, then you don't understand your signal. And you can't answer any of these questions. Like, this is it. And I still remember, it's like he would put his head to, this is it. Like, this is physics. This is science. It's this stuff. It's not like these fancy theories or whatever, like the little nitty gritty, like annoying stuff. And, there's this concept of the imperfections of experiment are necessary evil. I think one of your philosophers, Reichenbach, maybe said that, the imperfections of experiment are a necessary evil that we have to deal with. I think some of you might think that it's an unnecessary evil, but, I think your point was that it's actually not an evil.
It's real world.
It's a real world. This is it, and so this is really, I think, the essence of learning how to think like a physicist is going through this transition, and it really kind of flips everything on the head from what you think going into it.
Yeah.
All right. Well, thank you, Jim, for enlightening us with all of this. I'd love to open it up to questions from our audience. I'm sure there's many questions from people here.
Thanks. Hi. I know that there's a philosopher, Karl Popper, who makes the argument that he argues against inductive reasoning. He says that as opposed to coming up with theories and then trying to test them, that's not rigorous because our tests are inevitably biased by the fact that we want our theories to be true, and that instead we should, try to observe as much as possible and then try to come up with the theories to explain our observations. And I'm just wondering, I guess, firstly, what your thoughts on that are, and also how do you reconcile that with a field like cosmology where, by nature, you can't observe everything. You have to make decisions about what data to collect and what questions to look at. And how do you maintain the fact that your results are rigorous and not biased by the fact that you just want your theories to be true?
Right. Popper made an important start on the philosophy of physics. He was a little bit too rigid, though. He argued that if the theory fails a measurement, then it's been falsified. Toss it out. But of course, that doesn't apply in real physics. No. Maxwell's equations are wonderfully effective, yet they fail when applied to an atom. That doesn't mean you throw away Maxwell's equations. You turn it into a subfield, a good approximation, and you find a still better one that accounts for atoms.
Should we be worried about the bias that
Well,
trying to prove a theory when we set out to?
Yes. I think the main objection I have to Popper is simply his notion of falsification. We often use the word carelessly because all theories can be falsified. None of our theories is perfect.
And yeah, I think to add to that, and again, one of the themes in the labs, I'm sure you've noticed, is that it's the way to, like, when you're trying to test a theory, obviously you've got your own personal bias. Again, like a part of you, even if you try to be as objective as possible, part of you really wants it, especially if it's your theory, it wants it to be correct. But I think that's where the independent tests come in. You want to have as many independent tests as possible, and then you are really trying to convince yourself that you're not fooling yourself. And if the independent tests all give you, consistent results, then you can say, well, even if I'm being fooled, it's a pretty good being fooled. Like, it's pretty useful. Even if it's a trick, it's still pretty useful. And so I would make that argument.
My main question is, do you believe that the next sort of overarching great unified theory of physics that addresses the sort of disjoint between quantum mechanics and general relativity, do you think that theory is going to be a theory that simply meets the two in the middle and keeps many of the major details of both theories? Or do you think it's going to be an entirely independent theory that has both of those theories arise as an artifact of it?
I'd be surprised if it were the latter, because both of these theories are well tested, and you can't forget that. You'd better have a limit. For example, Einstein, when he felt he had finally his theory of general relativity, he immediately checked that it reduces to Newtonian mechanics in the limit where Newtonian mechanics is known to be a good approximation. Similarly, a new unified theory of the large and small scale physics had better reduced to those two theories in the two limits. That really constrains things. It's possible to imagine that some very different theory will reduce to Newtonian mechanics and to general relativity and the appropriate limits and to quantum physics and other limits. But if it's quite different from the theories we now have, it would be tough to make that connection. So my guess is, yes, it'll be a combination of space-time curvature and quantum physics. And of course, lots of attention is being paid to the fact that you could just apply the laws of quantum physics to the equations of Einstein, but it doesn't work out very well. So there's something missing. It could be simply a glitch in the way we think. We're frozen into positions.
Hi, I'm Claire. Thank you so much for doing this conversation. It was wonderful. In the beginning of your manuscript, you mentioned how when Einstein first introduced his theory of general relativity, people were very quick to jump on it and kind of assume some level of like believe in it despite, as you said, the tests not being extremely rigorous or independent for a while after the fact. So in that explanation as to like why people kind of jumped on it, you mentioned something about the theory of general relativity being very elegant, and I think that really stood out to me as like just a way that like people think about physics or math or like similar things as like, why do we have this inherent belief that if something is elegant, that means it would more accurately describe nature?
Well, it's a very good question. And, we're born with certain reflexes. A baby deer immediately tries to stand so it can run away if it's dangerous. A baby child, a baby person cries because it wants to clear its throat. And then, of course, it starts crying because it wants to be fed. So we have these reflexes, and who knows, maybe deep in our psyche, there is an appreciation for mathematics and for mathematical theories. I don't know. That's for others to decide. But the elegance of general relativity is a different thing to different people. To me, it is remarkable that in Maxwell's equations can be written as an action principle in which the action density is the simplest scale you can make out of an electric and magnetic field, or the equivalent 4-vector potential, that has the property that it conserves charge. It's a scalar field with a simple action and conserves charge. General relativity is the simplest theory you can write down that is a tensor theory that has the simplest of all possible Lagrangian densities, the Ricci scalar, and that conserves locally energy and momentum. Isn't that neat? I don't know when this was first realized, but to me, this is a remarkable fact that nature likes simplicity. Simplicity in a very abstract sense. And why do we appreciate that? Isn't that neat, we often say. Why do we say it's neat? I have to leave that to psychologists, I think.
I think one other element of elegance, though, is that Newtonian gravity didn't really explain the equivalence principle.
Right.
Right, that's a big question. Like, why do all masses fall? For Newtonian gravity, it just does. Whereas with Einstein's, he actually has some kind of more fundamental reason for it. So I feel like that's also an element of the elegance there.
Yes, yes. And that elegance was recognized early on. Einstein aimed for that. And of course, as general relativity developed, we started to see the same thing. In the years before 1960, I think the experimental evidence for general relativity was really weak, and everyone knew it. But everyone thought, gravity is so weak that I can't possibly do an experiment that will test it any better than the 3 classical tests. Of course, that was before people understood the power of electronics.
Hello, my name's Brad. Thank you for being here. And if you don't mind, I have a little bit of a more personal question.
Okay.
Which is, what is the second greatest honor you've received in your life?
The honor of being invited to sit here and talk to you. There's the other question. Which of your children is your favorite? You don't go there.
Hi, I'm Stefano. Thank you again for the talk. I guess I wanted to ask, if we were to find a final theory that reflected the objective reality, if it existed, what do you think it would look like? And I guess when I say that, I mean, do you think it would look like a single self-contained statement that could somehow generate the different quantities that we now know and can write down? Or do you think it would take the form of some arbitrary amount of discrete constants or statements, and something not as self-contained, I guess, if that makes any sense.
I must admit that I've not spent much time thinking about final theories because I believe that you can never demonstrate that your theory, no matter how deep and successful, is the final theory. Because, of course, you demonstrated that your final theory was not a just so story, and that means that it's experimentally substantiated, and experiments are always limited. So how do you know there's a final theory beyond your theory, no matter how good? People, of course, have speculated on what a final theory might look like. There's a book by Steven Weinberg, a great theoretical physicist, Dreams of a Final Theory, well worth reading. He specifies what the final theory might look like if current ideas more or less hold up. It will be a quantum field theory. It will be self-consistent. There will be no open parameters. It'll be unique. And read the book. I don't remember. I can't get too excited about final theories, as I explained.
Would it be fair to say that when, Steven Weinberg and Stephen Hawking, when the Stevens talk about final theories, they mean a theory that is not necessarily final in the sense that we know it is the truth and we will never be able to disprove it, but rather, like now we know what we don't know. We know that there's the small and the big, and we know that we can't bridge that gap. But if we come up with a theory to unify them, maybe we'll get to the point where there might be something we don't know, but we don't know that we don't know it. Like maybe that's what they mean by final, like in the sense that it just explains everything that we can see. And it's not necessarily, we can't say that it will never be disproved.
Right.
But we have no reason to.
We have no reason to, and of course, we should be satisfied. This theory accounts for everything we know. Why are you complaining? You're complaining because you don't know that it's really the final theory. And you'll never know. Live with it.
Yeah, what do you think physicists would do then? I feel like they would they just try to keep breaking it, or in more finer tests, or would they just retire?
Only when you reach a certain age. Some physicists, you can be very sure, will keep plugging away. I can do better. Many would find other employment. There is so much about natural science that we don't understand. Consider Bill Bialik in our department. He studies biophysics. Works wonderfully well about fascinating problems, but you just can't approach with a standard quantum physics. It's just too darn complicated. But it's good science. You're learning a lot about how these bugs move around, and eventually you'll learn about how to, the great demand from science these days is to find cures for our diseases. This is the century in which, we have certain lack of advance in the USA, but other countries are carrying the weight of research into fundamentals of biophysics that will teach us not only how to find a vaccine against COVID-19, but also against other diseases, the common cold even. There's so many things to do in all the other branches of physics. I feel, tread slightly on the toes of Bill Bialik by, in this book, refusing to countenance the word biophysics. You know that if you're a geologist, you have geophysics. If you're an astronomer, you have astrophysics. If you're a chemist, you have physical chemistry. Why did physics get into all these subjects? I think logically it's biophysics. It's not biophysics, it's physics. Or it's biology. But why have a name that couples two things that really must be done in different ways because of the degree of complexity of biology? it's excellent science in great demand, but it ain't physics because you can't bring tests of predictions that are as clean as what you get in physics. There are predictions in biology. Back to Mendel and the two pea flowers, inheritance. It works wonderfully well, but it's not a sharp prediction. And it can't be because it depends so much on the eventualities of how the germs develop. The complexity of real world can't be done. It's a different subject with different methods of research. And that will keep us going indefinitely, in my belief.
Hi, thank you so much for having this talk. My question is about, so currently the state of particle physics, the state of model has been very successful in describing everything that we see in particle colliders.
Right.
And a lot of the current theoretical focus in this field is like, people say like, it'll never be experimentally viable. For example, like strings, it's at the Planck length, they'll never be able to measure that. So what are your thoughts on like the current state of that field if so many of the theoretical ideas are like outside the reach of like experiments?
Yes. And there is a good rejoinder to that. Remember, Einstein took 10 years to develop general relativity, and then it took a half century to develop the technology to test the theory. The standard model for particle physics is far more complicated than general relativity. It's going to take longer. Oh, and there is a wonderful idea that behind quantum physics is what used to be called superstring theory. It's now strings or M theory. It contains in it limiting cases that have the structures of all of the known interactions. But of course, you can't specify how much, what are the parameters that belong to these interactions. They can't tell you because the theory doesn't have any constants to predict. It doesn't predict constants. So it's a theory. It also predicts the functional form of general relativity, but not Newton's constant. It can't. It doesn't have any constants in it. So it's very frustrating. Many people say, look, it took Einstein 10 years to find general relativity. This is a much harder problem. It's going to take us longer. They've been working on this problem since the 80s, let's say 4 decades. They still haven't got it, but they're not discouraged. Some physicists are plugging away at trying to see how to make this theory predictive. It could happen, or not. Maybe there's some other approach.
Hello. So you mentioned earlier this transition from undergraduate coursework to graduate coursework, specifically like how in undergraduate school you have structured and like solved questions, you know all the answers, whereas when you go to graduate school you get this jump where you don't even know if the question you're solving has an answer. And so I was having a conversation once with a peer of mine, and he was talking about how, so I'm sure you would agree, like all discoveries in physics happen with an aspect of creativity, thinking outside the box in a way that probably hasn't been done before. Yes. And my friend and I were talking about this idea that perhaps finding a new idea would require a new way of thinking outside the standard model of undergraduate teaching. So what are your thoughts on that idea that perhaps a different curriculum could pose more potential for students to think outside the box for a new theory?
Did she put you up to that?
No.
It's very difficult because to make a contribution to fundamental physics, you better know fundamental physics. And that takes a lot of learning. And so I don't know how you strike a balance between learning what needs to be known to understand what needs to be corrected and thinking outside the box at an earlier age. The hazard, of course, is you think outside the box and you reinvent the wheel at best, or else you go down some path that has already been explored and shown to be. So I just don't know how you balance that. You've got to learn the fundamentals, but you have to think outside the box. Those are two different goals, and how do you balance them?
I'm really glad you asked that question. I'm glad that there's interest in this question. And so there's a very, I think, Jim, what you're saying is that there's this idea that like, well, if you want to, before you get creative with something, you need to know the fundamentals of the thing first. That there's like the step. And to some extent, I agree. But I also definitely believe that there is a way to bring creativity into the classroom earlier. And that is, of course, what I'm trying to do with the labs. And because I think the lab is the only place you can do it as an undergraduate, because you have to do it. You have to get your hands dirty. But to give an analogy, I think that, saying that, well, you have to first learn all the theory before you can do any physics, and you have to wait 4 or 5 years until you get to grad school. It's like saying, okay, you want to play soccer? Great. Let's spend years learning how to dribble the ball, shooting on a goal without a goalie, pass back and forth in this super artificial. And then after 5 years of really perfecting every one of those, now you can finally play in your first match. Like, no, you want to get in the game, like at the beginning, right? And it might not be, a pro match with, the Euro Cup or the World Cup or something, but like you can have 5-year-olds kicking around a soccer ball and having the time of their life, right? So I kind of see like the undergraduate, introductory labs as that, where, you learn, and this actually brings up kind of one of my philosophies is like, a lot of students think that labs are supposed to help them understand the course content better, but I flip everything upside down. I say, no, actually, the class is where you learn the theory, but as soon as you learn even the most basic theory, you can go in the lab and test it.
And see it.
Right? Like if we tell you all objects fall at the same rate, the equivalence principle, how do we know? How do we know that that's true? Let's go in the lab and let's give you the opportunity to play around and actually try to disprove it. Like this is a very simple, and I think the nature of physics being so simple in many ways.
Yes, it
so
is.
Like that gives the access to very young students the ability to really play around with these ideas, even though we know the answer, right? Well, to our like a much higher level, I think even freshmen, even high school students, honestly, can like play around with the idea of physics, right? The philosophy of physics.
I love the vision.
Oh, wonderful. My goal has been with the labs as lab manager for 105 and 106 has been to, bring these ideas as early as possible. And 103 labs as well, and 104, the lab managers here as well. So, we try to give you the creativity opportunity to design your own experiments to answer questions. So I'd be really curious, either here or later, to hear, like, does it work?
I think it is working. Look at all this group.
Hi, thank you very much for your talk. At the very beginning, you told Dr. Visnjic that if we assume that there's some sort of ultimate, unified theory, then we can only get so close to it, but we cannot say that we've reached it. And that got me thinking from beyond like just simply a physics perspective, that when we talk about something as like defines everything, from a religious standpoint, like Stephen Hawking was famously atheist. We've had a lot of physicists who are religious from a diversity of religious traditions. So whether it's from a personal perspective or just like more talking about the subject, what do you see as the intersection between like religion and physics? Are they at odds with each other? Do they complement each other, or are they just separate spheres that don't really touch?
Good. This has to be dealt with. We have to think about this. I was raised in the Anglican Church of Canada. I was occasionally dragged to church. I hated it. What's this all about? I want to go out and play. It was a great solace to my mother, and I certainly don't. And now on occasion I do return to an Anglican church ceremony, and the words are beautiful. I never noticed that as a kid. I just wanted to get out of there. But yeah, it's an important element. I know physicists who are deeply religious, many who are outspoken atheists, sometimes with scathing opinions. Most of us fill the spectrum. But to me, the one thing that separates the two. Physics seeks what information that tells us about the nature of the world, reality. Religion relies on received knowledge. I think that's true, isn't it? And the received knowledge is something I've never liked. That doesn't mean it's wrong. It means that I never liked it. Furthermore, I do not think of any examples where religion has an impact, an effect, relevance to physical science, and I don't know of any physical science that is relevant to religion. I think you said it, they're separate. That's my opinion.
Well, thank you so much, Jim.